Good monad! We're here with Keon from Monad. You're listening to Interchain FM, the Cosmos radio station. If you're seeking alpha in the cosmos and beyond, look no further. I'm your host, Chango Unchained. I would like to welcome Keon, as we said earlier, to the podcast. This is new. Usually we have Cosmos people come talk about their projects or interoperability solutions, but this time we're branching off into the parallel VM ecosystem. Welcome.
Awesome. Thanks for having me, Chanko.
Yeah, it was great. So we met at SBC 2022, which is fantastic. I'm glad we met, and I remember you giving me the lowdown on Monad, and I was like, wait a minute, I've never heard of this before. This is like actually novel. Fast forward almost 2 years, you guys are almost close to mainnet. Soon, sometime this year.
Yep.
And in terms of parallel VMs, you're most likely going to actually make it work.
Yeah, I think there's been a lot of growth and interest in the parallelization space in the past couple of months, and there's a lot of dialogue right now, which is really healthy, about like Ethereum's architecture versus Solana's architecture. With Monad, we're trying to sort of deliver the best of both worlds between Ethereum and Solana. And we're doing that by rebuilding everything from the ground up to enable parallel execution, to enable high performance state access, or what we call parallel state access, which involves building a database from scratch, as well as a couple of other optimizations that altogether just result in a really performant, like fusion almost of Ethereum and Solana.
Okay, best of both worlds. By that, do you mean Monad is at once a monolithic chain, but also could be modularized, or something else?
I kind of left that vague. So maybe just to describe Monad from the start, Monad is a new layer one with high performance execution and consensus. Monad has over 10,000 TPS of throughput with 1 second block times and single slot finality. And Monad is fully bytecode EVM compatible. So you could take any application that's built for Ethereum and migrate the bytecode. There's like other things where like it's Solidity compatible, so you could like recompile it, but it still has changes. This is the stronger version, which is literally you could take bytecode from Ethereum and redeploy it on Monad, and it'll just work out of the box. Mm-hmm. And the reason that this is possible is because we've rebuilt the execution and consensus stack from the ground up in C++ and Rust, and introduced a couple of major architectural changes.
Architectural changes such as what? But before we go into the architecture, I understand that Monad is your proof of stake consensus is derived from hot stuff, which in turn was derived and inspired by Tendermint BFT. Mm-hmm. So talk about that. Like how does it iterate on legacy Tendermint? We interrupt this podcast to make an important announcement. Babylon Mainnet has launched, and Interchain FM is running a finality provider on the Bitcoin side. If you're an Interchain FM enjoyer and you have idle Bitcoin, then consider staking it and earning passive yield on that Bitcoin that would be otherwise collecting dust. You can do so trustlessly based on the Babylon protocol. Likewise, our Celestia validator is coming online soon, so if you'd like to support the Cosmos radio station so that we could keep sending you the alpha, the best way to do it is by delegating to our validator. We'd very much appreciate your delegation. Now, back to the show.
Monad's consensus mechanism is a derivative of hot stuff. Hot stuff originally is a 3-phase consensus mechanism. And I think one thing that's different between hot stuff and Tendermint is that hot stuff generally has linear communication, meaning that the leader sends block proposal directly to all the validators. So it's like the leader starts here and then fans out to all these validators, and then all the validators kind of send their votes to the next leaders, fans back in. Just due to the sort of design of the consensus mechanism, as well as the design of the fallback mechanism in the event of a timeout. Hot stuff doesn't require all of the validating nodes to talk to each other, whereas in Tendermint, all the validating nodes have to send votes to each other, which, if there's n nodes in the network that are participating in consensus, that means n squared communications in the case of Tendermint. Whereas with hot stuff, because all those nodes are not they're not talking to each other in the normal case. They're just forwarding their votes to the next leader. So it's linear, so it allows the network to grow to more nodes participating in consensus.
Linear complexity.
Exactly.
On the complexity scale, where does monad's consensus protocol fall?
It's also a linear complexity algorithm. So like I said, hot stuff is linear. Hot stuff has 3 phases of communication amongst the nodes. With monad's consensus mechanism, it's 2 phases. So there's a phase that's cut out due to the choice of the fallback mechanism, which I can talk about in a second if that's of interest.
Yeah.
And then also there's pipelining. So phases are kind of interleaved. So like when there's one block proposal that's in phase like 2 of its part, then the next block proposal, which is in phase 1, those 2 messages can be piggybacked on top of each other. So it's just like optimizations on top of optimizations to overall reduce the messaging complexity and allow the network to grow to more nodes. I think maybe like the kind of classic analogy that people give is it's like, Byzantine generals problems. So we have a whole bunch of generals that are like about to invade the enemy camp, and there's a commander who's actually going to give the signal of like, yeah, we're going to invade at 5 a.m. And the problem fundamentally is that, a couple of things. The generals are all like distributed, so they can't, there's latency in their communication with each other. And then aside from that, there's the potential that some of the generals are malicious and might actually be sending the wrong messages to confuse everyone else. But even just ignoring that part, like to talk about the reason why it has to be multiple phases in general. Imagine that you and I are both 2 of the like 100 generals that are like standing, kind of like located around an enemy camp that we're about to invade. And then the message arrives from the commander via carrier pigeon or whatever that you receive, and it says like, invade at 5 a.m. tomorrow. So you got that message, but the problem is you don't know that like I also got the message. So it could be that like only you got the message, and then if you go try to invade, then your forces will get slaughtered.
And I also know that it may not actually be from the commander?
No, you actually do know that it's from the commander because of signatures.
Okay.
So so
that's where the cryptography comes in.
Exactly. Yeah, the message itself is signed by the commander's private key, which you can verify was signed by him or her. Because of the asymmetric key cryptography. So you do know it's from them, but you don't know, the point is you don't know that I got the message also, and the other 100 people got the message.
Okay,
so that would be like,
I may invade alone and get taken down.
Yeah, so that's the first level of the problem. So then...
also what happens if there is an infiltrator general in the mix?
Let's skip to that a little bit later. Okay. That is a good question. So that you got a message that says invade at 5 a.m. So you can't be confident that I also got that message. So what do? We introduce an extra step where you send a carrier pigeon back to the general, who I keep switching from commander general, whatever, to the general that says, I acknowledge that I received this message and I'm planning to invade at 5 a.m.
Okay, so it's like this double opt-in process.
Right. So and again, you sign it with your private key, so like the general knows that it was really from you. So now the general has access to like all of these messages that everyone, like you, me, everyone else sent back. So the general knows the people got it, but that's still really not enough information. You have not gotten any more information. Like you just acted in response to that initial carrier pigeon. So then the general kind of aggregates all of those signatures into like a big message that just includes like your signature, my signature, etc., which we call a quorum certificate, and sends that quorum certificate out to each of us. So for example, now you receive this kind of like lengthier scroll with the pigeon that says like that I, Keone, acknowledged the message originally and like I'm planning to invade. So the question is like, do you now have enough information to be confident to invade? Do you or do you not?
Yes.
Okay, so the answer is you don't.
Oh, okay.
Right, it's a trick question. So why? So maybe you could talk about like why that isn't enough information.
Okay, so in comes the infiltrator, right? It's like somebody in the network who may have intercepted these.
Ooh, actually, we don't even worry about the infiltrator yet. Still, sorry. So
man, you're really testing my consensus knowledge.
It's just,
I thought I understood at abstract level, but when it becomes
yeah, well, it's hot stuff. And anyway, so the point, and it's a dumb example, but the point is that when you get that big scroll, the problem is actually, yeah, it is the infiltrator general is the problem. So the problem is that you might have gotten that scroll back, but the general might have only sent it to you and not to anyone else.
Okay.
Right, so like it's exactly what you said. Like the general is malicious.
Yeah.
So they decide to screw you over. So they send you the message with the quorum certificate. And so you invade, but I didn't get that message. So like I'm still like in limbo thinking like I don't know if everyone else is going to invade or not, so I'm not going to invade.
Yeah. Right. Okay. And how does the entire network of these people who are trying to invade come to consensus then? At what point is there enough information for them to move forward in the base case and not like just like realize it's an edge case and we have to like halt everything?
Yeah. So that's the great question, which is like it feels like things always can unravel from the last. Like when you get something, you don't know that you're not the only person that got it. Because if you were the only person that got it, then you would be in a more advanced state than everyone else is, which would be bad then because you would proceed when everyone else doesn't. Oh. So you're asking like, how is it that we can, in spite of the fact that there's always going to be some element of like, I got this message, I might be the only one. How is that okay? Well, that's where the fallback mechanism comes in. So anyway, so just to recap, the general sent a message saying invade a 5am. You signed a message. You signed an acknowledgement, sent it back. The general packaged all that into like a quorum certificate, sent you the quorum certificate. So now you actually sign an acknowledgement of that quorum certificate, send it back to the general. And then the general now prepares a quorum certificate of quorum certificates. So like it aggregates all these votes from that other phase, and then sends that out to us.
Right.
And at that point, when you receive that QC of QC, like quorum certificate of quorum certificate, you actually have enough information to know that you can proceed with the invasion.
And at that point, the general mines the block.
At that point, then you would execute the transactions that are in the. So now we have to switch back from
invade.
Then you invade.
And by invasion, that's finding a block.
That is finalizing the list of transactions in that block.
Okay.
Right, and so then you would invade, and similarly, like when I received that, like I would invade.
Yeah.
But also and anyway, the point is like the reason why QC of QC is enough to move forward is because of the fallback mechanism, which means that if we time out, like for example, if I don't get a message from the general, then I go and talk to all of my neighbors, to all the other
whoever's closest to you.
Actually, to everyone.
Everyone.
So it switches to like linear communication in the timeout case, like in the bad path.
Right.
And we all talk to each other, and we actually coordinate about like what the highest, like the most recent message we received from the general is, and then we like just kind of gossip amongst ourselves, and then once we get to 2/3 of all of us like agreeing that there was indeed a timeout, and also collecting the highest like thing that we've seen, then we message that out.
And then you proceed to invade.
Sort of. You message that out, and then you actually message that to the next leader, aka the next general, and that.
Oh, so everyone realizes that the last general timed out. Maybe he was killed or something for whatever reason.
Yeah,
so you moved on to the next general to figure out how to move forward.
Yeah, and then the next one can then repackage that information that we like coordinated on. And again, we're always like signing stuff. So the next general can take that like, it's called timeout certificate, but it's like a, list of, well, anyway, it's a list of signatures from all of us saying, we agree that the previous one, like, didn't send a message in time, so skip him. And like now the next one can now propose a block that's descended not from him because he got skipped, but from the previous one.
Yeah.
And that previous one is the one that has the enshrinement of like invade ROM.
Right. So, and in the proof of stake validator speak, that means one validator got skipped because they timed out, which results in like a missed block and like a lower uptime percentage that you can see from like looking at the block explorer.
Yeah.
And then next validator goes forward, and when they make a successful invasion, that is when they finalized a block, and then they are the ones receiving the reward of the block reward.
Right.
Okay.
Yeah, and I think it's also worth mentioning that all this is based on research from the DM team, actually.
The DM team?
DM, like Facebook's Libra/DM team.
Oh, Facebook Libra. I thought you were going to go all the way back to like Dwork Lynch Stockbuyers.
Yeah, no. So there's a paper that they published called Jolteon, which kind of describes this protocol, and then there's another paper, not by them, by a different group of researchers, one of who's on our team now, called Fast Hot Stuff.
Fast Hot Stuff. Okay.
But it's just like the same idea of like moving from 3 phases to 2 phases by introducing like that kind of timeout step that communicates about like the last known information, as well as the pipelining, which I didn't really mention, but it's like piggybacking messages from one phase on top of another one.
In pipelining, do you mean somewhere in the protocol it's informing how like orchestration of this communication is happening?
What it means is when we're in our analogy about like communicating about invading Rome, because that was like multiple phases, right? Like the leader sends like an instruction, aka block proposal, you send your vote back, then they send a quorum certificate out, you vote on that and send it back. So what I didn't really say is that those leaders are actually like different people. So the first time it's like Alice who sends you something. You send your vote to Bob. And then Bob aggregates that in a quorum certificate, sends that to you. You vote on it and send it to Charlie. But basically like, so you're doing all this stuff on Alice's block, but then when you send your stuff back to Bob, Bob is not only sending a quorum certificate on Alice's proposal, Bob is also sending a new proposal for the next block, like the next list of transactions.
Oh, that's different.
Yeah, so that's pipelining, because it's like because they're going to be sending you messages anyway, so they might as well like utilize that message to carry like more than one thing.
Gotcha.
And so yeah, so that's what it is. It's like Alice is the leader, and Alice actually proposes the block. You vote on it. You send it back to Bob. Bob aggregates your votes on Alice's block to make the quorum certificate.
Okay.
But also Bob sends you a new proposal for the next block. And so when you receive that carrier pigeon, you're receiving both the quorum certificate on Alice's block and also the new block proposal.
So now you can multitask.
Yeah.
Is this specific to Monad's consensus mechanism?
No, so this pipelining thing is also just part of the
part of hot
Jolteon, part of Jolteon and Fast Hot Stuff.
Okay, gotcha.
Yeah, but Hot Stuff itself is like an ancestor of both of those and does not have the pipelining.
Okay, all right. So, ladies and gentlemen, we've got state-of-the-art BFT proof of stake consensus now. Yeah. My knowledge of BFT would be, dates back to Tendermint, so that's like 7 years ago. Yep. But anyway, thank you for updating my knowledge of consensus protocols and proof of stake context. Moving on. So we've got consensus, and now we're moving up the stack to the parallel VM that Monad has innovated on.
Yep.
How does it work, and how is it different / novel compared to like either the Move VM or just the Solana VM?
Right. So a couple of things to point out. Monad's parallel execution is optimistic in nature. So that means that instead of having the transactions pre-specify all the dependencies and like scheduling work using all of that knowledge, instead of doing that, Monad just executes a bunch of transactions in parallel. So in monad, just take a step back, blocks are linear, transactions are linear within the block, and the job of execution is to get to the end state after executing those transactions one by one, as if they've just been run like serially, but hopefully doing something strategic, more smart. So the optimistic parallel execution, like just think of execution as a black box whose job is to deliver the end state after like running all those transactions. The parallelism is all under the hood.
I guess in the physical sense, it's no different than an Intel. What does Secret Network use to power its?
They use SGX, I think.
Yeah, I was thinking about SGX.
Yeah, it's not. I don't think it's like that, really, because also
when you said black box, I was like,
oh, sorry.
SGX.
Yes. So SGX is actually very controversial because it's been hacked.
Oh yeah, right. That was a few months ago, right? And Secret Network had to put out a statement about how the trade is actually secure.
Right. Yeah. So I don't think the TEEs, trusted execution environments, aka SGX, are pretty controversial. Not clear. But yeah. So when I say black box, I just mean like think of it as the job of the execution system is to like get to that end state. However, but you always have to get to the end state, but you could do it like by running transactions in parallel and be more strategic, which I should probably describe also.
Right. Let's bring it back to the EVM context, or even the Cosmos context, where like the base case is there's no parallelization and everything's sequenced one after the other, and so you have safety in that, however, not speed. Can't scale.
So in monad, there's still safety because the job is still to produce that same end result as if.
Well, right, yeah. The innovation of monad would be to retain the safety properties without sacrificing speed.
Right. Yeah.
And so that's why monad is potentially groundbreaking.
Yeah. Yeah, so the parallelism, maybe to give an example, so like say that there's 3 transactions, we're going to run all of them in parallel, and then before those transactions run, the state of the world is that I have 1,000 USDC in my account, and then transaction 1 is me sending 10 USDC to you, and then transaction 2 is like some unrelated transaction, like someone's minting an NFT. Then transaction 3 is me sending like 5 USDC to some other person, call them Alice. So again, transaction 1, I started with 1,000 USDC, and then I sent you 10 in transaction 1. And in transaction 3, I sent some other person 5. Right? So then in optimistic parallel execution, what we do is we actually just run all 3 of those in parallel as if they were starting from the same state. And we just keep track of all the inputs and outputs for that transaction. And then we generate something called a pending result, which is like keeping track of the inputs and outputs. And we step through those pending results, and we just commit pending results as long as there are no conflicts to them. Where conflict means that one of the inputs has since mutated. Yeah. So like in the context of the example I gave, it would be like pending result 1 has an input of my USDC balance is 1,000. That's the input. And then the output is that particular piece of state changes to 990. Yeah. Because I deducted 10. And yours went from like 0 to 10 also, but ignore that part. And then transaction 3, because it's being run in parallel, so it doesn't know about transaction 1, so it would also have an input of my USDC account as 1,000. And then the output would be that USDC account goes to 995. So we have these pending results that we generated, and then we're stepping through them. So we go to pending result 1, we can commit that one without any issue. We go to pending result 2, we can commit that one without any issue. But then when we get to pending result 3, there's a problem because pending result 3 has an input of 1,000. But now we know that like since then it's mutated to 990. Right.
So what you're describing sounds like this like branch transactions, kind of similar to how UTXOs on Bitcoin work. So you've brought that into the account-based world. without actual UTXOs.
Yeah, I guess that's one way of thinking about it. It's like generating you're right that the example that I gave seems a lot like a UTXO because it's like I'm going from 1,000 to 990. I'm going from 1,000 to 995. And you could imagine that there are like those two Bitcoin UTXO transactions. But then when we go to merge them, the earlier one always takes precedence.
Right, yeah.
Right, so the earlier one will commit without issue. Mm-hmm. And then the later of the two actually needs to be redone because the input was wrong. So the premise of this whole computation was wrong. Mm-hmm. So we go re-execute. Right. And then at that point, the input is 990 and the output is 985.
Yes, got it. I could visualize it. It's like here's the original input and then branches out to here, new output, and then like branches to here and then here subsequently.
Right.
And this is the final mutated state.
Yes.
Okay.
And so just to point out a couple of things. One is that we're stepping through the pending results in the original order of the transactions. We're trying to commit them.
Based on where they are in the mempool or how?
Oh, based on the official ordering of the transactions in the block.
Okay, and
because the official ordering's already been determined.
Oh, by the protocol?
Right.
I see. Okay. By dictating that programmatically, you're reducing any ambiguity with MAV or like validators becoming malicious and trying to like reorder transactions?
Monad is a leader-based consensus mechanism. So the leader has the authority to choose the ordering and sends it to everyone else, and then everyone else like votes on that, and once they agree on that official ordering, it becomes enshrined in the history of the blockchain. Mm-hmm. What I didn't mention, which I probably should have, but it's okay, is that there's asynchronous execution in Monad. So,
asynchronous. Okay, so okay, all right. Let me just contextualize it so that people understand. In Tendermint BFT, which is, fair enough, no longer state of the art for proof of stake, right? We got like 200 TPS. Tendermint proof of stake is it's a partially synchronous network. And an asynchronous network is something like Bitcoin, where the miners don't necessarily need to ever even know who's online or whatever, but they could like gossip transactions and formulate blocks based on that in approximately 10 minutes of time. So in this case, you're achieving the same properties of having an asynchronous network like Bitcoin, but in the proof of stake context?
Yeah, the asynchronicity that we're talking about is probably different from the one you're talking about.
Oh.
Yeah, but when we say, it's a phrase we made up though, so to be fair, we might have just like, reused
so you're not talking about asynchronous networks?
Yeah, we're not talking about like the asynchronous assumption about the time for the communication to complete, which I think is like in Tendermint, it's like partially synchronous assumption.
Yeah.
So we're not talking about that.
Oh, okay.
So asynchronous execution. We also call it deferred execution. That might be actually a better phrase.
Okay.
But basically the idea is the nodes come to agreement about the official ordering of transactions without executing. And then after the consensus completes on that block, then two things can happen in parallel. One is they start doing consensus on the next block. And the other thing is they execute the block that they just consensused on.
Yeah.
So essentially execution is in a separate swim lane. It's another form of pipelining, actually. It's like, but actually I should tell you the reason why this is really important. So in Ethereum, the blocks are 12 seconds, but the approximate time budget for execution is about 100 milliseconds, which is only 1% of 12 seconds, right? It's a very small amount of time. So it's basically like this time dilation factor that's happening where only 1% of the block time can be expended on execution. And the reason for that is that consensus is expensive because consensus requires like nodes all around the world talking to each other. Communicating around the world is like 200, 300 milliseconds. So consensus realistically just takes up almost all of that time. So there's very little time set for execution. And execution has to complete before consensus in most blockchains where there's interleaved execution and consensus. Now with Monad, we don't have that. So execution is
segregated them.
Yeah, execution is not a prerequisite to consensus. So the nodes, when they talk to each other and they like come to agreement about an official ordering, they do that without having executed yet. which is really great because then it means that once that consensus completes, now we can move on to the next block of consensus. But in parallel, now we can take that whole block time to execute the thing that we just agreed upon. So this massively raises the time budget for execution.
Raises the time budget, or you mean like reduces the
it effectively raises the time budget for execution, because instead of only being able to allocate a small portion of the block time, we can allocate the full portion of the block time.
Gotcha. This is great. We've dug in so deep to on the technical details, like probably more so than what a lot of listeners may potentially be interested in, because we've basically given you a rundown of basically like the monad white paper, essentially in 15 minutes or less, which is great. But let's move up a level to the application layer and talk about that. So last I checked, you tweeted that Monad had over tens of digits of applications already preparing to launch on Monad. Mm-hmm. Can you talk about that?
Yeah, I think I last tweeted like 70 or something.
Yeah, that's like a significantly high number.
Yeah, it's a lot. So there's a number of projects that are redeploying existing Ethereum applications on Monad because Monad is fully bytecode compatible. And they're excited about being able to scale to many more users than they have right now.
Right, and get faster time to finality as well as, is it cheaper gas or something?
Correct. So just maybe to give an example, like a Uniswap swap on Ethereum costs like $5 to $50 on Ethereum mainnet right now. Actually more. I checked today and it was like $150. Which is insane.
It's a surge period.
Yeah, we're like Bitcoin just hit 62K or whatever. So, it's like very congested right now. Mm-hmm. But even when it's not congested, it's still like $5. And then on Ethereum layer 2s, that same transaction costs like 10 cents to $1 or a couple dollars.
Yeah, but the problem is the liquidity is fragmented from the main chain.
I mean, even 10 cents is a lot though, because I mean, it may be not a lot to like
10 cents per transaction is a lot.
It may be okay for like a swap, but then if you consider that like an order book, every single one of those transactions of a market maker adjusting their quotes.
Right, you need to cancel it, and it adds up to just a...
Yeah, if every single one is 10 cents, it's their market maker is gonna spend like tens of thousands of dollars a day maintaining all their quotes. Yeah. Which is way too much. Mm-hmm. So with Monad, there's like basically 100x reduction in cost from the L2 level, which is already, like a 50 to 100x reduction from mainnet.
Right. And that's why, I was talking to the work team. They were excited about Monad because it allows them to have cheap cancels because they're a limit order book. Mm-hmm. And so Monad seems to be the best contender to be hosting that application. Mm-hmm. When you mentioned Uniswap, was that an example, or is Uniswap actually going to deploy
that's an example, because Uniswap swap is like the most prototypical.
Sure.
And everything should be done in terms of gas. So like a Uniswap swap is about 100,000 gas. That's like 100,000 units of compute. So it's like
gas?
Yeah, so like on Ethereum, all of the compute is metered. Mm-hmm. The more complex the transaction, the more gas it expends. Right. And then people pay a gas price, which is like the amount of ETH they're willing to pay per unit of gas.
Right. And so it's like gas price denominated in ETH equals GUI times unit of compute, or like number of bytes.
Right. Yeah, I think gas is actually a really confusing name.
Yeah.
Because it should really be called compute units. And then you should be paying Ether. You should be like, I'm willing to pay like 0.0001 Ether per compute unit. Mm-hmm. It's almost like Ether should be called, instead of called Ether, it should be called gas or something. Mm-hmm. I'm just saying that gas is like a really confusing name.
Yeah, I get it.
Because gas is not a unit of work.
Right. And so this is like part of the thing that I was like, okay, so every single bull market, there's the climate change fudders who look at Ethereum gas, and they're like, because it cost X amount of ETH, like significant dollar amount of quote unquote gas in ETH, that NFTs are contributing, negatively impacting the environment, but not really, because it's actually, gas is arbitrary. Because like within the EVM, they arbitrarily assign certain costs to certain compute Whereas,
Right.
and it's like, it's almost the inverse, where certain things that take up a lot of compute, they've priced it like really cheaply. Whereas like certain things that should be really easy, they've priced it really expensively. And so the gas cost that you're perceiving is actually not a good measure of what's actually taking up a lot of electricity.
Yeah, I mean, a lot of blockchains nowadays is kind of a publicity stunt almost. Just say like, oh, we're carbon neutral or whatever, and they just buy carbon credits.
Yeah.
But yeah, in a proof of stake chain, I feel like the overall electrical costs are not substantial.
Right.
Like, it's not proof of works. You're not incentivizing people to like, burn electricity to secure the network. It's a different thing.
Totally, and like the amount of energy that's actually expended, it's almost fixed, like as a validator, right? You've got like a fixed cost of electricity / how much you're paying AWS or whatever.
Yeah,
whatever cloud provider.
It just made me think about like, I wonder how Bitcoin miners are doing right now, because I feel like they always
I think they're doing really well.
Yeah. Whenever the price goes up really fast, then it's really good for them because
because then the economics make sense for them to turn on the miners again, whereas before the fixed cost, like the lower bound of cost, doesn't actually match the price of Bitcoin, and so you're like operating at negative EV at that point. But then now, because the EV is so high, people in countries like Africa and South America with access to like thermal or water or any types of renewable energy, now they're like building things to harvest that energy to mine Bitcoin, which is interesting, right? It unlocks the natural energy sources that would otherwise go unused around the world. Anyway, I digress. Back to Monad. What sorts of applications are, you said 70 plus applications at this point. You guys are going to see mainnet sometime this year, and so once mainnet goes live, all of those applications are ready to be turned on. What types of applications are those?
It's a mix of, I would say like over half are DeFi applications.
Sure.
And then the remainder are mix of like NFT, marketplaces, social-fi, gaming, sports betting, on-chain betting.
Yeah, I would say that on-chain betting falls into, I guess, DeFi or like degen speculating category.
It's definitely degens, yeah.
How many gaming applications do you see coming through? The gaming is a big thing. It's like a big narrative, and I'm seeing more and more projects launch games on chain, but then I just fail to understand what part of the blockchain they actually find useful. I mean, we did a gaming panel at the Atom Denver 2, Atom Denver Squared, and talked about the utility of games. And what we discovered is that if you were a game, like an indie game creator, it could potentially make sense for you to break into the gaming industry by distributing like an IGO, like an initial game offering, and basically have like allow for the crowd to invest in like the IP of your game, and you could distribute your game that way. And if it were kind of like this open source paradigm that other people who are shareholders of the game could then build mods on top of it and like create value that way. And you're incentivizing the distribution of this game by like taking royalties off of each distribution as well. So that could potentially be a very interesting use case for blockchains and the intersection of gaming.
Yeah, it's a great point. I feel like the problem with all of these things is just the incentives, like making sure that it's not like, oh, someone raises money for a game but then doesn't deliver the game.
That's the edge case.
But I feel like there should be a way to like deal with that with some sort of like lockup on the fund release that's
like
contingent on like a council of like observers who like look at the game assets and are like, oh yeah, it looks like you're 25% to like building this game, so here's 25% of the funds.
Right. Yeah, that would be good. Yeah, we need more self-regulation into space. I think there's not enough. I mean, there's a bunch of. I mean, there's more than enough DAOs, but there's not enough actual DAOs that self-regulate us, and that's the reason why we've fallen into traps like Luna UST and that kind of thing, because it's just like yield farming run rampant, and it hasn't changed. It's not changing this cycle. It's not going to change. People are still yield farming. right?
That's true, yeah.
Yeah,
no,
people,
I mean, the
people
number,
are restaking,
yeah, that's
rehypothecating
true.
the same.
Yeah, Blast has
underlying.
2 billion
Yeah.
TVL right now.
And now the dangerous thing is people are yield farming, or restaking is a huge thing, right?
Mm-hmm.
But the problem is the underlying staking token secures the network.
Mm-hmm.
So if you're restaking it to farm eigenlayer tokens or whatever token, Blast or whatever, then it's not actually going back to secure the network. All things considered, Monad, potentially game-changing, very exciting. What are the milestones that you're looking forward to that people should be watching out for? Obviously, anyone watching is going to have questions about the token, so I think that's the most exciting thing.
Yeah, I think I'm just excited about launching the testnet and the mainnet this year, and then also just really excited about the growth of new applications that are being built by ambitious builders, building things that can ultimately cross the chasm to mainstream adoption, and are facilitated by really low fees, really high transaction throughput, kind of like unlimitless building potential in the new Monad environment.
Yeah, exactly. So now in this generation, which is next gen blockchain scaling, we have Monad. You're the leader in parallel execution, and then we have modular blockchains, which the leader of is Celestia. I think the ETH people like to say it's ETH, but no, it's Celestia. Okay. Yeah, great, very exciting. So in terms of timelines, when can people look out for public testnet? When mainnet, if validators want to join, any information that you have to give there?
Yeah, we're expecting public testnet sometime in Q2, and then mainnet by the end of the year.
Well, it's been great to have you on, Keon.
Yeah.
I'm sorry, I keep saying Keon, but it's Keone.
Keone, yeah.
Keone.
No worries, you can call me whatever.
Good morning to you, and good night to all you alpha seekers.